Good afternoon. Good afternoon, and welcome to the third lecture in this series of the world of electrical engineering. And today we have the honor of listening to Professor Shai Avidan. Shai got his undergraduate in computer science degree from Bar Ilan. Then he moved to the Hebrew University, where he did his PhD with Amnon Shashua. And then he has a lot of experience with companies. I think he was in Microsoft, Mitsubishi, Adobe,
too many.
Mobileye, yes, I know. And he joined the Faculty of Engineering in 2009, and recently became an associate professor. So we will hear about the rise of seeing machines.
Thanks. Thanks for the introduction. Show of hands, everybody here undergrads or grad students? Undergrad students, raise your hand. Okay, good. So, I'm working in the field of computer vision, essentially attaching a camera to a computer and doing something with it. What would you like a computer to do with a camera? It's a question to the audience. Why would you need that?
Confirm an identity, or maybe analyzing the space, the area.
Okay, what for?
For navigation of a machine or robot.
Okay, good. So the hope is that by the end of this talk you'll realize there is actually a huge market for computer vision applications. And the question is, can we deliver? We as engineers, can we deliver on that promise? And the answer is not clear. There is a lot of potential. There are starting to be a lot of companies that sell products that are based on computer vision, but there is still much more to do. And I thought that what I'll do today is give you kind of a brief review of the history of computer vision, where we are today and where we're heading to. And the last part is the most fuzzy one. No one really knows how the future will look like. So that's a seeing machine. There is a computer, there is a camera attached to it, and we're done. And in fact, that's how people perceived the problem many years ago. In fact, the story goes that in the mid-60s, MIT wanted to build this human artificial intelligence, and they assigned one of their brightest students, Simon Pepper, to build a visual system. And they gave him 3 months to build that system. And he came back at the end of the summer and reported that it failed. He couldn't build a visual system that will recognize and behave like the human visual system. And the question is why? Why is it so difficult? And the reason is that there is a huge variability in objects surrounding us that we take for granted in resolving the ambiguity. For instance, this koala bear, it's shown here under different illuminations, different object poses, in clutter. It's partially occluded. There are different types of bears viewed from different viewing angles. And still we have no problem perceiving this object and recognizing it as a bear. And the question is, can a computer do something like that? And there's been a lot of work trying to build systems, seeing machines, machines that can detect and analyze a scene and give us meaningful information. So what is computer vision used for? There are two main broad areas of interest for computer vision. One is to measure things, and the other is to provide perception, to recognize objects in the scene. What do I mean when I say measure? This is the typical pipeline where you're doing vision for measurement. You start at the top with a bunch of images of a scene, and you end your way down here with a 3D model of the object. And you can imagine all sorts of applications. For instance, there are applications for inspection. You build a 3D model of something, and then you want to take pictures of it and make sure that the 3D model created is just like the CAD model that was used to create it. You have engineering tasks where you build buildings. You want to see that they fit the definition of how they were supposed to be constructed. You take pictures. You want to recover them. In aerial photography, you want to build maps and terrain models of the Earth. You take satellite images. You take aerial photography. And you use all those images to recover 3D models of the world. And then you use them for navigation, for instance, or some other applications as well. So that's kind of very large, broad field of computer vision that I'm not going to discuss in this talk. What I'm going to talk about is vision for recognition. And the holy grail of computer vision in that sense is being able to take a picture like this and do that. Being able to say that there is sky on top, it's an amusement park, it's actually Cedar Point in California, wherever it is. There is a Ferris wheel in the center. There are people standing in line. There are people on the ride. What are the objects? What are the activities? And so on and so forth. There are so many different things that you can say about the image. We as human, and the computer is not able to do that yet. So the question or the goal of this talk is to show us where we are on our way to achieving a system that can do something like that. So in order to figure out where we are, let's see how the smart people of Hollywood figure the role of computer vision. So that's the Terminator back in 1984. And that's how people then perceived computer vision systems. It's a moving a robot that can detect, analyze objects. And at that time, it was considered sci-fi, right? It was considered impossible to do. Well, is it? One of the early attempts to solve computer vision problems was through something called neural network. And I'm going to show you how industry and academia play hand in hand. Back in 1986, there was a very influential paper by these guys, in particular, the second author, Jeff Hinton, I'll refer to him later, and they devised a method to train something called a neural network. Now, what is a neural network? It's essentially a system that takes an image like this, the number 4, and plugs it into the input layer, propagates it through some hidden layers, and then outputs the number 4, or the number 5, or the number 6. And what Hinton and his colleagues did, they devised an algorithm for achieving this goal. And what can you do with something like this? Over the 90s, there was a surge of interest in optical character recognition, and what you see here is a system that takes as input an OCR, a number written in an image, and what you see here is the output of this neural network. Okay, the number 9, 0, 1, and so on and so forth. And this was developed by Jan LeCun, another famous computer vision researcher at AT&T Research Labs during the 90s, and it achieved very good results. And actually, this is used today. If you drive on Kvish 6, on Highway 6 in Israel, it's a toll road, and you don't need to stop at toll booth. The camera takes a picture of your license plate, registers the number, and sends you the bill by mail. And actually, the university gate also has an automatic system that detects numbers and lets you know if you can enter the campus or not.
Let the guard know.
Let the guard know, that's true. So neural nets have been very successful in being able to solve this type of recognition tasks, but they were very slow. Just to give you a sense of the speed, in 1995, a neural net-based algorithm would be able to detect a face in an image, but it would take it about 3 hours. Okay? So the recognition rate was reasonable. It wasn't perfect, but the time was completely inadequate. No one would use something like that. And then, in 2001, two researchers from a company, Mitsubishi, came up with an algorithm for face detection. And the algorithm they presented ran in real time and gave very good results. And the basic thing they did was very simple. They said, we're going to pose this as a binary classification problem. Essentially, given a window patch like this, the question is there a face here or not? And in order to answer this question, what they did is they multiplied this face with this filter. Essentially what they did is they looked at the pixels here and they summed the value of all the pixels here. They looked at the pixels here and subtracted the value of all the pixels here. And if the value was above some threshold, then it's a face. If it's not, then it's not a face. And they did it using multiple filters. I'm using here only 2. In practice, they use something like 6,000 filters. And the nice thing about this algorithm was that it ran in real time. And it gave very good results. The interesting thing is that to be able to train a system like that, you need to collect a lot of data. And by collecting data and training the system, you get the good performance. And when the first systems came out, it was around 2001, and there was a demo booth, and I walked by and I tried the system on myself to see if they were able to detect my face, and they failed. Care to guess why? Actually, no. That's not a joke. That's not a joke. I'll refer to it in a minute. Why did they fail recognizing my face?
Glasses.
That's a good point. No, actually they trained on glasses. Well, it turns out I'm bald. I was bald then as well. And the system didn't recognize people because if you look, the first filter is somewhere here, but the second filter starts looking at this region of the hairline. And because the first systems didn't have that information, they simply weren't able to recognize me. I later found out that the main source, going back to this Japanese thing, the student who collected the data, they told him to collect data of images. That was in the early 2000s. And the first place he went to was some Japanese porn site. And I don't know why. And so there was a strong bias towards Japanese women in the first face detection algorithm. In fact, HP had a lot of bad PR several years ago because they failed to recognize black people. And it went back to the problem of the database that they were using for training didn't have enough black people. And therefore, there was like, the computer vision algorithm is discriminating against black people in all their user interface applications. Amazing. And so here are the results. This is a slide from the original paper by Viola and Jones. And you see it does a decent job detecting all the faces as well as this one here. Now, how does the algorithm work? Well, I've shown you the previous slide. I'm showing you a window, an image patch, and I'm asking you this binary classification problem. Is there a face here or not? Well, imagine that there are about 1 million patches, 1 million windows in this image. Essentially, you take this window, you slide it over the entire image. At each image location, you ask the question, is there a face here or not? So out of the 1 million patches that are in this image, it got right all the faces, and it made only one mistake. So is this considered a success or not? It's certainly much better than what was used before. People are striving to remove even this amount of outliers. You want to get perfect result. And systems are getting better and better. There's been steady improvement in the quality of face detection. It also depends on the pose of the face, if you're looking frontal or sideways, and so on and so forth. There was a talk by a Google executive, a Google engineer a couple of years ago, and he said that if we have about 20 pictures of your face from Facebook, Google Plus, or something like that, we can recognize you more than 99 point, I don't know how many nines, behind it. So the quality of face recognition systems really improved over the last decade. And this is not considered a solved problem, but today you will not even think about buying a digital camera without a face detection application built in, right? That's an expected feature in every system, and it started showing in 2003 or 2004. That was one of the first biggest success of computer vision applications, because it was something useful, something people wanted, and something that computer vision was able to deliver. And in fact, you're using it, or it enables other technologies you don't even think about. So people here probably use Google Street View. Google Street View had to deal with privacy issues, and the way they deal with it is by blurring out faces and license plate numbers. So if you use Google Street View, you'll notice that the license plate number are blurred out, as well as faces are blurred out. So these enabling technologies of face detection, of license plate recognition, allowed Google Street View to become ubiquitous as it is today. And of course, it makes errors like the errors you can see here, which really goes back to the way that this face detection algorithm works, right? All the algorithm does is looking at a small window and asking the binary question, is there a face here or not? And clearly here what you would like to do is take context into account, and there is a lot of work in recent years of adding context. Well, actually this is a sign and therefore I should not blur the sign, or this is a picture on a wall and therefore I should not blur it, and so on and so forth. But there is a lot of work specifically on face detection and then adding context in order to be able to give better and better results. And then in 2005, there was another very influential paper by a guy named Navneet Dalal and Bill Triggs from France, and they wanted to solve the pedestrian detection problem. And they did something that we do in signal processing all the time. They said, well, we want to detect this guy over here, but we're going to change representation. And that's something that we do all the time. We move from the time domain to the frequency domain. We move from the time domain or from the image domain to Haar representation, to Haar wavelets, which wavelet is just another representation of a signal. Here they moved from the pixel domain to the space of histograms of gradient. So that's yet another representation of the original signal. And the claim is that in this representation, it's much easier to detect a pedestrian. Why is that? Because this representation is invariant to the different color of the cloth, and therefore you can get a much better separation between a pedestrian and a non-pedestrian. And again, the question is, this is a binary classification problem. Given this window, you ask the question, is there a pedestrian here or not? And the previous representations, the ones using neural nets, the one using Haar wavelets, did not give good answer. This representation, however, did, and still the theory behind it is fairly fuzzy. It's not clear why this representation is so good. In practice, it works extremely well, and you can see typical results of such a system. So these are extremely difficult scenarios because you see people at different poses, they are partially occluding one another, and still this is the type of quality that some of the most recent pedestrian detection algorithms are able to provide you. But we want to go even further than that. So far I told you how to detect faces and people because these are the most important things to us as computer users. In the last decade or so, there's been a push for pixel labeling. What is pixel labeling? What you want to do is you want to take a picture like the one shown at top and label each and every pixel in the image. So this is the set of classes you have. Blue is cow, sheep, sky, and so on and so forth. And you want to automatically be able to take this image and translate it to something like that. There is a body here, there is grass, there is road, sky, there are trees, and so on and so forth. So that was a paper in 2007 by a group of researchers from Microsoft Research. And it was one of the early successes of pixel labeling problems. They gave very good results, and the question is, what is it good for? Well, they went silent for a couple of years, and in 2009 came out the Kinect. Now the Kinect, as you might know, is based, the first version is based on a camera developed by an Israeli company called PrimeSense that was recently acquired. The irony of things, it was bought last month by Apple, but it originally provided the camera for the Kinect system. And the Kinect system basically is able to infer the body pose, and you can play games based on that. So they use the pixel labeling algorithm that I've shown you, the results that I've shown you in the previous slide, to do a pixel labeling of the human body and learn the skeleton of the object. And here is a visualization of how their algorithm goes. It was published in 2011, only after the Kinect came out, and we were able to understand what these guys did. So again, what they did is they did a couple of things. The first thing, they did away with the pixel values. They didn't use the intensity, the image itself. What they did use is a depth value. So what you see here is a depth map that the Kinect captures. And then they went ahead and did pixel labeling, and that's what you see here. And the regions that they had were not sheep, cow, grass, and so on and so forth. It was the different parts of the human body. You want the head, the torso, the right hand, the left hand, and so on and so forth. And they collected a huge amount of training data. They asked people to come into their labs and play in front of the Kinect. They recorded all that information. They had people painstakingly marking all the pixels as the different body parts. And given that information, you can infer the skeleton of the player. And that's the input that you, as a game developer, can have access to. You can see the top side and the front, side, and top view of a skeleton that is mimicking the action of the actor there. Okay?
Who developed the algorithm?
So I don't know how to make the distinction between PrimeSense and Microsoft. This is the result of a paper by Microsoft Research. That, to the best of my knowledge, they developed it. The paper I've shown you, this one came also from the same guys at Microsoft Research in 2007. So apparently they took the depth map that PrimeSense gave them and developed a skeleton inference engine on top of that. The irony is that with version number 2, they switched from PrimeSense camera to a different camera based on a different technique, based on time of flight, instead of structured light that the first generation used. And the claim is that the second generation gives much cleaner and better results. We'll have to wait and see. Kinect was the fastest selling gadget, I think, in the history. They reached $1 billion in sales in less than 60 days or something like that. It was really phenomenal success.
All these similar technologies are done here in Israel.
So, yeah, I should probably point out that there is now a huge, everybody is betting on, it's called the natural user interface. Now that we're in the post-PC era, people don't want to use keyboards and mouse. They want to interact naturally with computers. So Microsoft has a large research group that is devoted to doing this type of things. Intel has a huge push to perceptual computing, I think it's called, where there are large labs here in Israel that deal with basically equipping every Intel-based computer with a camera. And the camera is, as I've shown you in the first slide, it's not enough to output pixels. You want to output, for instance, the detected faces. You want to output the detected people, their pose, to let people base their algorithm on top of that. So Intel has a lot of work on that.
Answering to a question, maybe it's worth mentioning that the CTO of PrimeSense is a student of alumni of our.
Yeah, ex-student of Hardin.
Ex-student of.
Former student of Hardin.
No, no, former student of mine.
Well, but also of Hardin.
But Inon.
No,
Inon was
my student.
Oh, I see.
CTO was my student.
Okay.
He graduated about 5 years ago. So maybe it's even...
So we have both CTU and CEU.
Yeah,
You know what's here?
they're both with Apple now.
CTO.
And CTO behind the technology. Was Alex Front was my student.
And I'll be remiss if I will not mention Mobileye, where I used to work back in the day. And what Mobileye does is develop camera systems for the automotive market. And I pulled an old video of Mobileye back from 2005, and it shows you the type of capabilities that the system can have. So this is a camera mounted on the dashboard of a vehicle looking outward, and it automatically detects there are zebra crossing here. It detects all the people, all the pedestrians. It detects the vehicles in the scene. Everything is done in real time. It detects the lane that the car is driving in. The person at the right in front of the camera is marked in red. That's the person in the most dangerous to the camera, or the car is the most dangerous thing for him. And the system runs in real time, and you can imagine that this input can be fed back to the driver and give him an alert if he's too close to the person or too close to the vehicle, or is drifting off lane, and so on and so forth. So that's the type of quality you can achieve in the industry today. That's a clip from 2005. The performance only improved since then. And it brings together a lot of technologies. You need to be able to have cameras that use low power, chips that can work with low power, and the amount of false rate should be extremely, extremely low. You can't give false alarms, and of course you can't miss a pedestrian. I haven't talked about the need to work in video, so you need to process 30 frames per second, and in fact video can help you because you can integrate information over time and make better decisions if from a single image you have a questionable result. So this is the type of result that you can get from a computer vision application.
Also measures the distance.
Yeah, so no, the system, that's actually this. So the system uses just a single camera. And the point is that you don't, the problem with using two cameras, that's, the reason you want to use two cameras is you want to mimic radar systems. The problem is that the calibration of a stereo camera goes off quickly. And if you think about a camera that needs to survive in a vehicle for years to come without proper maintenance, it becomes extremely difficult to do that. And if you get the calibration wrong, then all your measurements are wrong and the system will fail. So you want to avoid that actually, and you want to use just a single camera. So you can rely basically on the geometry of the position of the camera with respect to the ground. If you can estimate the ground plane, then you can, by triangle inequality, you can figure out the distance. And Amnon Shashua, when he was asked about it, his usual reply was, well, Moshe Dayan was able to drive with a single eye. There is no reason for cameras not to do the same.
Well, they were also stealing a single eye.
That's true. Well, he did a lot of things, Moshe Dayan.
So you have an idea of another story?
In this system, did they use comparison between two different frames, or did they use one frame at a time?
So from a single frame, you can extract all the information, and what you learn in classes here, for instance, is how to do filtering in time. How do you? There are all sorts of. It's called Kalman filter or particle filter. There are all sorts of tools. There is a principal way of approaching the problem of getting measurements over time and integrating them in order to infer the correct state of the world at each time step. And if you go willy-nilly and just guess your way around, it might work for a couple of sequences, but it will not survive a real-world production system like that. So the next thing I wanted to show is we can do phase detection, we can do pedestrian detection, we can pretty much do object detection if you want to focus on a particular object. So vehicles is an important class. People have developed object detection, vehicle detection. People wanted to detect pedestrians, they developed pedestrian detection. Another aspect that people wanted to do is a way to organize all their data. And this falls under the category of image retrieval. And the way to solve this problem is to borrow, or should I say steal, ideas from the text retrieval community. And that's nice because what people did in computer vision, they went and looked at how Google is doing text retrieval. Google took it from the text retrieval community, and the way it works is as follows. You have a document and you want to find similar documents. You don't compare word by word. What you do is you build a histogram of words. And then comparing two documents boils down to comparing the histograms of the two documents. And this is counterintuitive, at least for me, because what it means is that you throw away the position of the word in the text. It's no longer important. All you care about is, does the word China appear here and here? If so, then these two documents are slightly similar. And if out of 100 words, 70 words appeared in both documents, then these two documents are probably on a very similar topic. So what people in computer vision wanted to do is borrow this idea and apply it to computer vision. Well, how do you do that? Well, the way you do it, you take an object or you take an image and you throw it into what is known as a bag of words. Okay? So you take an image and you break it into all these different words, visual words, and different objects will map to different histograms. So you have your world of images on top, and you build a dictionary of words at the bottom. And now you say, well, this image of a person, the histogram of visual words will be very high for this type of visual words, but will be very low for these guys. And similarly here, and similarly here. Well, this begs the obvious question, well, we know what's the dictionary for words. For text, how do you do it with the vision system? How do you do it with images? And the answer is that nobody really knows. So there was a sequence of papers that the only thing that differed from one paper to the other was the size of the dictionary. One guy suggested a dictionary of 500 visual words, the next one suggested 5,000, and it went as high as 1 million visual words. And the way you build visual words is very similar to vector quantization that you might learn in other courses here. And essentially what you want to do is something like this. You have a lot of training images, and what you see here is for each column, these three examples were mapped to this visual word here. So this visual word here is this guy, this guy, this guy. And likewise here, and you see that all these guys are very similar to each other. And likewise here. So the idea is that you want to construct a visual dictionary of all these atoms, essentially, and then each image is reduced to a histogram of objects like this. And once you have reduce the image to histograms, then all the tools developed in the text retrieval community can be used here in order to retrieve images and give you the result that you want. So this is a typical example. You see the image at the top, and these are the actual code words that were computed ahead of time, and this is a mapping from this image to a histogram of this code word. And if there will be another image of a car, then the other image of the car will have a very similar histogram to this one, and therefore the similarity between the two will be very high, and therefore we will be able to claim that the two images are the same. And again, note that we're doing the same thing we did over and over again. Instead of using Haar wavelet, we're using histogram of gradients for pedestrian. And instead of using histogram of gradients, we're using now histogram of code words. Always the idea is to take the representation which is not convenient for manipulation and move to some other representation that is better suited for our needs. And here is just a visualization of a couple of interest points detected by the system. And the first and most influential paper on that topic on how to detect feature points came out in 1999. And because of lack of time, I will not go into it, but you can trace back this paper to the heat equation in physics from a couple of hundreds years ago. If you read the paper, it's how the interest point behave. It's like the extrema point in a heat equation. And here is, so in 2003, people took this idea and applied it to computer vision. It was a paper by a group from Oxford. And I'm showing you here the results. What you see here are frames from the movie Run Lola Run. And what the user does, he marks the yellow rectangle at the left, and you see a zoom in here. And what the algorithm needs to do is retrieve all the images in the video that have this particular patch in it. And you see here the retrieved images. Here you see the actual frames, and here you see the zoom in of the yellow rectangle. So why was it able to do that? Because you can see here all these circles. These are the visual words that he detected for in each image. He did the same thing here. I'm not showing you here the visual words. So the claim is that this thing is similar to this thing because the histogram of visual words here is very similar to the histogram of visual words here, and here, and here, and here. And this is what lets you retrieve images. How am I doing? Oh, okay. And here are examples of the algorithm. You can have large-scale retrieval. You see the query image on the left and the retrieved result on the right. And you can imagine a tourist guide on a mobile phone. You take a snapshot of some place, and the algorithm retrieves the most similar image from the web and tells you it's the Aachen Cathedral. And you can do the same thing with movie poster recognition. Actually, there is a company called Coaba that allows you to do that. You take a snapshot of a poster, and it gives you where it plays right now, and if you want to buy a ticket or something. Google Goggles is something that allows you, for instance, this is a nice application that combines several things. You take a snapshot of text, and it automatically does OCR, detects it in German, and translates it into English, for example. Okay. And of course, object recognition in the wild. There was a recent application of a leaf guide. You take a snapshot of a leaf, and it tells you what leaf it comes from, and you can do it with birds as well. And there is a big push for visual shopping. You saw this shoe, and you like it, but not quite right. You want to see other shoes, and they are sorted here by likeness. So these are other shoes that are similar to this one, based on color, on shape, and so on and so forth. So this is all based on the same principle of bag of words and matching histogram of code words in order to help you shop easier and spend more money. Just one more example. You can do auto annotation. You dump all your images on the hard drive, and the system automatically figures out who appears where, connects each landmark to the relevant web page, so you have much richer database to browse through when you want to use it. Okay. So what now? The current rave in the field of computer vision is something called deep learning, and here is a prefix to this. How do you measure all these algorithms? You have people mark images and say this is a vehicle, this is a windshield, this is a wheel, this is a window, and so on and so forth. And this is a crowdsourced project that started in 2005 at MIT, but there are many groups now. And you simply ask people to spend time do that, and people do it for free. Sometimes they're not doing the right thing. But still, it's amazing how much content you can collect. They have hundreds of thousands of images that are labeled and marked like this. And there are annual competitions. Every group can compete and show how well it can detect and recognize objects in these images. And last year there was a big surprise. There was a group called Supervision who got an error of 15% compared to the best known method, which was 26%. And what did this guy do? What they did is something called deep learning. And if you recall the beginning of the presentation, I've shown you a neural net. This is nothing more than a neural net on steroids. And the only difference from 1986 to today there are two differences. the computers got much more powerful and we have much, much more data. And not surprisingly, it's Jeff Hinton, the guy who invented backpropagation for neural nets in 1986, who proposed this system. And sure enough, last year Google bought him, essentially. These are his two PhD students. They proposed this system, and Google bought him, I think, earlier this year. And Jan LeCun, the guy who did the license plate recognition using neural nets, he's a professor at NYU. He developed similar systems. And last month, Facebook announced that they bought him too. So essentially, there is the period from academia to industry is getting shorter and shorter. The development in computer vision is becoming very relevant to companies like Google, Microsoft, Facebook, and the like.
Should we be worried about you?
No. I was on the dark side. So what's next? Clearly, computer vision is going to play a role in advertising. If Google and Facebook knows the content of the images, they'll be able to offer you targeted ads, targeted products. There are going to be autonomous vehicles. That's pretty obvious. The question is not if, it's when, within the 5-10 years.
This is a headline.
So Google has one. Mobileye has one. This is the Israeli. This is Mobileye's. This is an article from New York Times. There is actually an autonomous vehicle in Israel driving from Jerusalem to the Dead Sea, hands-free, based on a single camera. Stay away. Well, it's a very expensive car. It's an Audi A7. It's a beautiful car. Exactly. There is the Google Glass, but I think about it as a personal assistant. It opens the door to many different applications. If you have a camera looking at whatever you're looking, the possibilities are endless. If it's a strong enough, powerful enough camera, it will be able to detect and see things and alert you, even without you being aware that you want that. And it can see much further in whatever weather conditions and so on. So that might be a very powerful thing. And last but not least, going back to the what is computer vision, I think there is now a surge in 3D printing, and in order to print something, you need to capture and measure something. So maybe computer vision can be used for that as well. So computer vision, there is a rise of interest in it. Hopefully you can join the revolution as well. That's it. Thank you.
Are there any questions? Yes.
Will computers be able to cross-referencing information?
Yeah.
Not only pictures, but taking information from Google? And
yeah, that's known as multimodal. There is a lot of work. You can. People have proposed system where you type the word banana, and it goes to Google, retrieves the top 200 images of banana. Hopefully they are good enough, trains a system, a vision system on top of that, and now you have a banana detector for images. And you can imagine doing it for every different word. I don't know this is the perfect system for that, but people are thinking a lot about these cross modalities. Yeah?
How adept is that technique? Because if we with progress in every direction, maybe in a couple of years we'll have higher separation technology for imaging, and then we'll have to build the dictionary all over again.
Yeah, that's an open question. There are two things. Do you want to separate dogs from cats? Do you want to separate different breeds of dogs? And so on and so forth. People are building systems. The main goal now of computer vision is being able to build a system that can separate between thousands of categories. It's assumed people in natural language processing hypothesize that there are about 80,000 different categories of objects. I mean, if you open a dictionary and look at all the nouns, there are about 80,000 different objects in the world that you can attach a name to it. So the goal of computer vision is to be able to recognize each and every one of these 80,000 objects. And it's not clear how to do that. I mean, we know how to build a banana detector or an apple detector, but it's clearly not feasible to build a linear system that will go over each of these 80,000 different categories and say, is it a banana, is it an apple, is it an orange? You want to kind of do it at once. And this is still an open question how to do that.
That's it.